Myself, Dr. Anupama Marwaha. I am Associate Professor at SLITE Longowal. The topic of today's lecture is analysis of continuous time signals. First of all, what is a signal? A signal simply represents a set of information or data, and it is a function of one or more independent variables. Now, the independent variables can be either time or space. So, if the independent variable is time, then the amplitude of the signal can be plotted as a function of time. That means, amplitude will be varying as a function of time. So, if the independent variable is space, then the value of the signal will be varying as a function of space parameter, that is distance, as it is shown in this diagram. Now, the examples are, if the independent variable is time, then the example is, say we have a sinusoidal signal. So, here we can see a sinusoidal signal in which the value of the signal, that is varying sinusoidally with respect to time. The various characteristics of a sinusoidal signal can be amplitude, frequency and phase. So, the example of independent variable as space is the picture signal. So, here we can see this is the picture signal in which the brightness, that is varying as a function of spatial variables, that is x and y. So, other examples of signals can be, we can have electrical signals like voltage, current, electromagnetic signals, acoustic signals, video signals, noise signals, or we can have biomedical signals and so on. So, there can be a large number of types of signals. Now, if we consider electrical signal in this lecture as a function of a single independent variable, that is time, then the various parameters which can be used as a measure of size of the signal can be signal strength, signal energy and signal power. So, we will define all these parameters one by one. So, what is signal strength? Signal strength, it is determined simply by measuring the area covered by a signal. So, let us suppose that we have a signal xt as an exponential signal, then the strength of the signal V will be the area covered by this exponential signal, that is the integral of the signal over the whole time domain. So, integral of xt dt from minus infinity to infinity will give us the strength of the signal. The next parameter is signal energy. Now, in electrical systems, the signal xt, that can be either a voltage signal or a current signal. So, let us suppose that we have a continuous time voltage signal Vt as the value of xt, then the total energy dissipated in a resistor over the time interval t1 to t2, that is given by integral of v square by r dt, because as we know that the power that is given by v square by r. So, the energy is the integral of power. So, the energy will be instantaneous energy, that will be integral of v square by r dt. So, if the value of r is taken as 1 ohm, then we define it as the normalized energy. So, in general, for any signal xt, the normalized energy, the signal energy, that is normally the normalized energy. So, the normalized energy will be determined by integrating the signal xt, square of xt from minus infinity to infinity. The next parameter is signal power. So, first of all we will define instantaneous power. Again, if we have, suppose we have xt as the voltage signal Vt, then the instantaneous power dissipated in resistor R, that will be defined as Pt, which is equal to Vt into It, or it is equal to V square T by R. So, again if we take the value of resistance as 1 ohm, then the normalized power, that will be equal to V square T. So, in general, for any signal xt, either it is Vt or It. So, let the generalized signal be xt, then the normalized power, that will be given by limit t tends to infinity 1 by t integral of xt square dt. So, here why have we taken this, we have included the time period also, and we have taken the limit as t tends to infinity, because this is the general expression for normalized power. So, we can define it either for periodic and non-periodic signals. So, we will later on see what is the difference between the two. So, how signal energy and signal power, they are defined for periodic and non-periodic signals. Now, there are large number of classifications of signals. So, we can classify the signals as real valued and complex valued signals, single channel and multi-channel signals, single dimensional and multi-dimensional signals, continuous time and discrete time signals, analog and digital signals, periodic and non-periodic signals, deterministic and random signals, energy and power signals, and even and odd signals. So, we will discuss all these classifications one by one. So, a real valued signal is that which takes on the real values. For example, we have the sinusoidal signal which takes on the real values, and the complex valued signal is that which takes on the complex values. So, the example is complex exponential signal. The second classification is single channel and multi-channel signal. So, single channel signal is that which is generated by a single source. For example, we have a function generator. Now, multi-channel signal is that which is generated by multiple sources. For example, we have the ECG signal. The next classification is single dimensional and multi-dimensional signal. So, if we have a single dimensional signal, that means the signal which is a function of only single independent variable. For example, we have the audio signal in which the speech signal amplitude, that is a function of time. Now, if the signal it is a function of multiple independent variables, then it is called multi-dimensional signal. For example, we have the television picture signal, which is a 3-dimensional signal in which the brightness at each point that is a function of space parameters, that is x and y, and it is also varying as a function of time. So, a picture signal xt is a function of x, y and t. So, these are 3 dimensions. The next classification is the continuous time signal and discrete time signals. Now, a signal which is a continuous function of time and is defined at all values of t, that is called a continuous time signal. That is a function which is available at every value of t. For example, this is the exponential signal in which it is varying with respect to time continuously. Now, discrete time signal is that which is defined at discrete intervals of time. So, again if we have the same signal, exponential signal, then its corresponding discrete time sequence can be defined as a small a raised to power n, that is here the value of n can be 0, 1, 2 and so on, that is the value of the function, value of the sequence x n is available only at discrete intervals of time. Now, the next classification can be continuous valued signal and discrete valued signal. So, continuous valued signal is that which can take on infinite number of values on the y axis, and discrete valued signal is that which is defined only at finite number of values. Now, using these two categories, you see using the continuous time signal, discrete time signal and the continuous valued signal and discrete valued signal, we can have 4 different combinations. The first combination says that we can either have continuous time and continuous valued signal. So, a signal which is available at every instant of time, that means the signal which is varying continuously with respect to time and it is also continuous on the y axis, that means it can take infinite number of values, then the signal is said to be continuous time and continuous valued, and this is what is basically an analog signal. So, an analog signal is that which varies continuously with respect to time and it can take on infinite number of values. The second possible combination is we can have continuous time discrete valued signal, that is if it is continuous on the x axis, that means it can take on infinite number of values on the x axis, but it is discrete valued, that means on the y axis it can take on only discrete number of values, then it is continuous time discrete valued signal. The next combination is we can have discrete time and continuous valued signal, that is if it is varying, it is defined at discrete intervals of time, but it is continuous on the y axis, that means on the y axis it can take on infinite number of values. So, this is the example of a sampled signal. The last combination can be discrete time and discrete valued signal, that is if the signal is available at discrete intervals of time and it can take on only discrete number of values. So, this signal is basically what is a digital signal. So, that means if we want to classify the analog signal and digital signal, then we have to see whether the signal is continuous or discrete on the x axis and the signal whether it is continuous or discrete on the y axis. So, analog signal is that which is continuous on x axis as well as y axis. So, signal, so we will define analog signal is that which varies continuously with respect to time and can take infinite number of values. Similarly, for a digital signal it has to be discrete on x axis as well as on y axis, that is a signal which can take on finite number of values at discrete intervals of time. The next classification is periodic and non-periodic signal. Now, signal that repeats after regular intervals of time, that is called a periodic signal. For example, if we have signal xt, so if xt is equal to xt plus t naught, where t naught is the periodicity, that means the signal xt will be repeating after t naught time period. For example, we have sinusoidal signals, we have cos signal or sine signal. So, it can be seen that both the signals they are having periodicity of 2 pi. So, these are the examples of periodic signals. Now, non-periodic signal is that which does not repeat itself, or we can say that a signal which repeats after infinite interval of time, that is the time period that will be infinity. That means, if the signal repeats after infinite time period, or practically it is not repeating, or we can say mathematically we can say that x t is never equal to x t plus t naught for finite values of t naught. So, example is we have this exponential signal. So, we can see that it is not repeating till t is infinite. Now, these are few examples. We can extend the definition of periodic signals for combination of a number of periodic signals. For example, if we have two periodic signals, say this is the first sinusoid, this is the second sinusoid, sinusoidal signals, these are the periodic signals. So, what happens to the sum of the periodic signal? In this case, if we take the sum of periodic signals, it can be seen that it is again periodic with a time period of s by 3, it is 1 by 3 seconds. And this is another example in which we have again two sinusoids which are of different frequencies, and here the resultant is again periodic with a time period of 1 second. Now, is it that the sum of periodic signal is always periodic? No, the sum of periodic signals, it may not always be periodic. So, we have to find out what is the condition of periodicity for sum of periodic signal. So, in order to find out that condition, let x t be the sum of two periodic signals x1 t and x2 t with time periods t1 and t2 respectively. Now, if we want x t to be periodic, then let capital T be the time period of that periodic signal. Then for this signal to be periodic, x t plus capital T should be equal to x t. So, if we substitute here x t plus t in this expression, so it will be say x1 t plus m1 t1 plus x2 t plus m2 t2. Now, if we want it to be equal to x t, so here that means m1 t1 should be equal to m2 t2 and let it be equal to t naught, some fundamental period. So, if we solve this expression, what do we get here? We get here t1 by t2, that is equal to m2 by m1. So, m1 and m2, these are some integers. So, that means for x t to be periodic, the ratio of the time periods t1 and t2 should be a ratio of two integers, that is it should be a rational number. And if x t is periodic, then how can we find the time period? The time period will be determined by taking the LCM of t1 and t2. For example, we will discuss two examples. For example, let x t is equal to cos of t plus sine of under root 2 t. So, both are periodic signals. Here we can see that both are periodic signals. So, the first signal x1 t, this is periodic with time period. We can find the time period of this periodic signal. So, this will be t1 is equal to 2 pi, and in the second case, that is for the signal x2 t, the time period it comes out to be 2 pi by square root of 2. So, if we take the ratio of the two time periods, that is t1 by t2, here it comes out to be square root of 2, which is not a rational number. That means, though the individual functions x1 t and x2 t, they are periodic, but the sum of these periodic signals, this is non-periodic. So, the next example is let x t be cos pi by 3 into t plus sin pi by 4 into t. So, we can again find out these are the periodic signals. So, we can find out the time period. So, t1 it comes out to be 6 if we solve it, and the time period for the second periodic signal it comes out to be 8. Now, if we take the ratio of t1 and t2, this is 6 by 8 or it is 3 by 4, which is a rational number. So, this is what is the condition for periodicity. We have seen that for the sum of two periodic functions to be periodic, the ratio t1 by t2 should be a rational number. So, here this condition is being satisfied. So, x t is periodic. So, in this case the signal x t it comes out to be periodic. So, once it is periodic, now we have to, the next step is that we have to find what is the periodicity. So, the periodicity or the time period of the resultant signal, that will be the least common multiple, that is LCM of t1 and t2, that is the LCM of 6 and 8. So, it comes out to be 24. Now, the next classification is deterministic signal and random signal. Now, the signals which can be completely specified as a function of time, they are called deterministic signal. So, there is no uncertainty associated with these signals, or we can say that the deterministic signal can be expressed by a mathematical expression. It can be expressed mathematically. For example, we can have sinusoidal signal, rectangular signal, exponential signal and so on. for which we have a mathematical expression. Now, random signal is that which cannot be described by a mathematical expression, that is which is not predictable with respect to time. So, naturally there will be uncertainty associated with its value, and hence the random signal is characterized statistically. So, for example, we have noise signal. The next classification is energy signal and power signal. So, energy signal, as we have defined earlier, the signal energy. So, energy signal is that which is having finite energy and 0 power. So, the corresponding energy is then given by the expression as we have earlier defined. This is the integral of square of x t from minus infinity to infinity. And what is a power signal? So, power signal is that for which the energy tends to infinity and power is finite. So, the signal power again as we have defined earlier. So, it is the limit 1 by t integral x t square dt from minus t naught by 2 t naught. Now, depending upon the periodic and non-periodic signals, the expression of power that can be simplified. So, the examples are all the non-periodic signals, they are generally the energy signals, and all the periodic signals, they are generally the power signals. So, if we have a periodic signal, that means now the expression, this expression will be reduced to the expression in which we have to integrate over the time period t. So, for a periodic signal x t, the signal power will be determined by solving this expression. The next classification is even signal and odd signals. So, even signal is normally it is also called a symmetric signal. So, a signal x t, it is said to be even if it is invariant under the transformation t to minus t, that is x of minus t is same as x t, that is an even signal, it is equal to its time reversed value. So, for example, we have this cos signal. So, it can be seen that for the positive and negative time domains, the value of the signal that remains unchanged. Now, odd signal is that which is, you see, which satisfies this condition, that is x of minus t, that is equal to minus of x t, that is it is equal to the negated time reversed signal, that is whatever is its value for positive time domain, then for the negative time domain its value that gets reversed, it is negative of that value. Example, we have the sine signal. Now, any signal in general can be expressed as a sum of its odd and even signals, that is if we have x t signal in general, then we can express it in terms of its odd and even parts, where the odd and even values can be determined by solving these expressions. The even part of x t will be determined by evaluating x t plus x of minus t by 2, and the odd value, odd part of the x t signal will be x t minus of x of minus t divided by 2. So, function whose even part is 0, that will be a totally an odd signal, and if we have a function whose odd part is 0, then it is an even signal. For example, let us discuss one example. Let f t be an exponential signal which is existing only for the positive time domain, then this function, this signal can be expressed as sum of its even and odd parts. So, what will be its even part? So, even part will be that for which the positive and negative time domain values should be the same. So, it is this function. So, its corresponding odd part will be the signal which is having the value whatever is its value for positive time domain, then for negative time domain its value gets reversed. So, this is its odd part. Now, if we take the sum of these two signals, the resultant will come out to be the signal f t. Now, many times we have to deal with complex signals in which you see they might not be always in the form that we want to have, or it may be required to generate complicated signals from the basic signals. So far we have been talking only about the simple signals. So, what can we do if we want to generate some complicated signals from the basic signals? So, in order to enhance the understandability and applicability of signals, what we can do is we can perform some basic operations on the simple signals. So, in general, let us suppose that t is the transformation that we are applying on the basic signal x t, then the resultant signal will be y t. So, we will see what type of transformations we can apply. The basic you see signal operations, they can be either performed on the dependent variable or on the independent variable. So, first of all we will discuss about the operations which can be performed on the dependent variable. Now, in this transformation the y axis value that will be changed, but the x axis value that will remain unchanged. So, the various operations are amplitude scaling, addition, multiplication, differentiation and integration. Now, what is amplitude scaling? Now, amplitude scaling, it is performed on the signal to vary its strength, that is the signal yt will be represented as alpha into xt, where alpha is the scaling factor. So, depending upon the value of alpha, the signal will be the signal strength that will be varied, that means either the signal will be amplified or it will be attenuated. So, if the value, let this be the signal xt. So, if the value of alpha is less than 1, let it be say 0.5, then the signal gets attenuated, and if the value of alpha is greater than 1, then the signal will be amplified, as it can be seen in this case. The value of alpha is 1.5, the signal xt that gets transformed into 1.5 times xt y to t, that will be 1.5 times xt. So, it is amplified. The next operation is addition. So, addition of amplitude of two or more signals that is performed in this operation at every instant of time. For example, if we have signals x1t and x2t, then yt will be the sum of x1t and x2t at every instant of time. So, the resultant yt is x1t plus x2t. The next operation can be multiplication. So, multiplication that determines the product of amplitude of individual signals at every instant of time. So, yt signal, that will be the product of x1t and x2t. The next operation is differentiation. So, if we have the basic signal xt, then we can differentiate the signal xt, the resultant signal will be yt. So, this is the signal xt. So, if it is differentiated, we get the transformed signal yt. The next operation is integration. So, if we have signal xt, we can integrate the signal to obtain yt. Now, the second category of operations that can be performed, that is on the independent variable, that is the, in this case, the periodicity of the signal that will be varied, that means the value on the x axis that will be changed, whereas the amplitude or the strength that remains constant. So, the various operations that can be performed, they are time scaling, time reversal and time shifting. So, we will see one by one how these operations are performed. Now, what is time scaling? Let us suppose that we have signal xt, then time scaling will be done by multiplying the value of t by a factor, scaling factor a. So, it is a times t. So, its result will be that it will either result in compression or expansion of the signal xt depending upon the value of a. So, if this is signal xt, then if the value of a is greater than 1, say it is 2 in this case, if we find out x2 of t, then the signal gets compressed, and if the value of a is less than 1, in this case it is 1/2, then the signal will be expanded. So, it can be seen that the here in this case the value on the x axis that will be changing, whereas the amplitude that remains same, that is the value on the y axis that remains unchanged. The second operation is time reversal. So, time reversal, it will simply flip the signal around the y axis, about the y axis. So, if we have signal xt, so yt will be x of minus t. This is signal xt. So, we have simply reversed about, we reverse the inverse the time signal, inverse the signal about the y axis. The next operation is time shifting. The time shifting operation, it results in shifting of the signal on the time axis. So, if we have signal xt, then xt minus t naught will be resulting in the signal yt. So, if the value of t naught is positive, then the signal will be shifted towards the right and it is called the delayed signal, and if t naught is negative, then the signal will be shifted on towards the left side on the time axis and the signal is said to be advanced. For example, here we have signal xt, if we give the value of t naught as 2, then we have xt minus 2. So, it can be seen that the signal has been shifted towards right and signal is said to be delayed. Now, we can also perform the operations simultaneously. It is also possible that if we have the signal xt, then we can perform multiple of operations together. For example, if we have here time shifting and time scaling operations performed on the same signal xt. So, we have x a t minus b, then in this case we have to follow some precedence rule. For example, here if we take out a outside, then first of all time shifting will be performed and then time scaling will be performed to obtain the transformed signal. Now, apart from the basic signals, there are certain elementary signals which play an important role in the analysis of communication systems. We have to study about some elementary signals which are useful to check the performance of system. So, what are these signals? So, we have, you see, unit step signal or unit step function, unit ramp function, unit impulse function, rectangular pulse function, signum function and sampling function. So, what is unit step function? Now, unit step function is that which takes on a value of unity for the positive time domain and its value remains 0 for the negative time domain. So, it is represented as ut. So, ut is equal to 0 for t less than 0 and its value is 1 for t greater than 1. Now, why is it called unit step function? Because of unity value for the positive time domain. So, the utility of this signal is that it can be used to represent any signal in positive time domain. For example, if we have an exponential signal which is to be defined only for the time domain, a positive time domain, then we can write it as a e raised to power at multiplied by ut. The next function is unit ramp function. So, unit ramp function is that which varies linearly with respect to time. So, ramp function ramp t, that is equal to t for positive time domain and its value is 0 for negative time domain. Now, why is it called unit ramp function? Because its slope is unity, and the unit ramp function, it is the integral of the unit step function. So, it can be represented in terms of unit step function also. The next function is very important function for communication applications, that is a unit impulse function. Now, unit impulse function is that which exists only at t is equal to 0, that is if it is represented as delta t, then this function will be existing only at t is equal to 0, and at this value of t, the value of the function will extend to infinity, and at all other values of t, the signal unit impulse function that will have 0 value. And why is it called unit impulse function? Because the area covered by the unit impulse function is unity, or the strength of the signal, that is 1. So, a unit impulse function is having unity strength, that is the integral of delta t dt from minus infinity to infinity, that is equal to 1. So, example of another unit impulse function is, here we have 5 delta t minus 1, that is this is an impulse function of strength 5 and it is delayed by 1 unit on time scale. So, it is delta t minus 1. So, we will have an impulse existing at t is equal to 1 and all other values of t, its value will be 0. Now, there are basic properties of impulse function which are useful for solving number of integrals in communications. The first property says it is the sampling property or the sifting property. So, according to this property, if we have to solve the integral gt multiplied by delta t minus t naught, then this will be simply equal to the value of the function at t is equal to t naught. So, we need not go into the derivation of how we have obtained this, but it is a property using which we can directly solve this integral. Now, an extension of this result is, if t naught is equal to 0, then what will happen? The integral f t delta t will be equal to f of 0. That is, if we have delta t multiplied by any function f t, then this integral will be simply equal to the value of this function at t is equal to 0. The next property is scaling property. Scaling property, it says that if we have a scaling factor in a unit impulse function, then it is simply equal to 1 upon a mod delta t minus t naught. The next property is the replication property, according to which if we take the convolution of a function, any function with unit impulse function, then it is equal to the function itself. The next function is rectangular pulse or gate function. So, rectangular pulse function, it is represented as RECTT or it is also written as pi t. So, this is a function which takes on a value of unity in the time domain from minus half to half, and for all other values it is 0. So, it is similar to a gate. So, that is why it is also called a gate function, and the limiting case of rectangular pulse function is an impulse function. For example, here we have a rectangular pulse function whose area is unity. In this case, it is extending from minus tau by 2 and its value is 1 by 2. So, that the area is 1. Then as we reduce the value of tau to 0, what will happen? The width of the pulse, that will go on reducing. So, if tau is being reduced, so 1 by tau, that will go on increasing. So, what happens if tau that becomes equal to 0? If tau is equal to 0, the width will be equal to 0 and the value of the function will be extending to infinity, which is equal to a unit impulse function. The next function is signum function. The signum function, this can be defined as the function which takes on a value of 1 for the positive time domain and it is having a value of -1 for the negative time domain. It can be expressed in terms of unit step function also. So, in terms of unit step function, it is equal to 2 times ut minus 1, or it can also be written as ut minus of u of minus t. The next function is called the sampling function or sinc function. So, this is a function which is basically it is sin t by t, that is it is sin pi t by pi t, that is it is a sinusoidal function whose peak amplitude is reducing with increasing value of t. So, as value of t that goes on increasing, the peak amplitude of sine function that goes on reducing.